History remembers the weapons that changed wars, but often forgets the ones that arrived too early to be understood. Scattered across the 20th century are machines so radical, so ambitious, that they defied the technology, doctrine, or politics of their time. Some were built in secrecy, others canceled in fear, and many dismissed as failures before their true potential could be realized. These were not mere experiments, they were glimpses of futures that never fully materialized. From aircraft that anticipated stealth decades ahead to vehicles designed for nuclear battlefields, this is a journey into the boldest ideas military engineers ever dared to pursue. Horten Ho, 229, the stealth jet conceived before radar warfare. The Horten Ho 229 stands as one of the most startling examples of a weapon that arrived decades before the world was ready to understand it. Conceived in the final years of World War II, this radical German aircraft abandoned the traditional fuselage and tail layout in favor of a pure flying wing. At a time when most fighters relied on brute engine power and conventional aerodynamics, the Ho 229 pursued efficiency, speed, and survivability through shape alone, challenging nearly every assumption of mid-20th century aircraft design. Designed by brothers Walter and Reimar Horten, the aircraft was developed to meet the Luftwaffe's urgent requirement for a fast, long-range jet fighter bomber capable of penetrating Allied airspace with minimal interception. Its sleek, tailless form dramatically reduced aerodynamic drag, allowing it to achieve impressive speed and range despite the crude jet engines available in 1944. More remarkably, the flying wing configuration naturally minimized the aircraft's radar cross-section, an unintended but profound advantage at a time when radar was only beginning to influence aerial warfare. The Ho 229's construction methods further hinted at stealth principles that would not be formally defined until decades later. Due to severe shortages of strategic metals, the airframe relied heavily on wood, bonded with charcoal-infused adhesives. These materials absorbed portions of radar energy rather than reflecting it, reducing detectability compared to conventional metal aircraft. Combined with its smooth contours, lack of vertical stabilizers, and absence of external protrusions, the Ho 229 produced a radar signature significantly smaller than that of typical World War II fighters. Flight testing revealed both extraordinary promise and serious risk. Early prototypes demonstrated high speed, agility, and stable handling, suggesting the flying wing concept was viable even with early jet propulsion. However, engine failures, limited pilot visibility, and chronic reliability issues proved difficult to overcome. As Germany's industrial infrastructure collapsed under Allied bombing, resources and time ran out before the aircraft could be refined or mass-produced. The war ended with the Ho 229 still in the experimental phase. After the conflict, surviving components were seized by Allied forces, with one unfinished airframe eventually transported to the United States for study. For decades, the Ho 229 was regarded as an unusual technological dead end. Modern simulations and radar testing, however, have reframed its legacy. Evidence now suggests it would have been significantly harder to detect than its contemporaries. In retrospect, the Horten Ho 229 was not just advanced, it was a premature glimpse of stealth aviation, decades ahead of its time. Buran space shuttle, the autonomous orbiter the world wasn't ready for. The Buran space shuttle remains one of the most ambitious and misunderstood technological achievements of the Cold War. Developed by the Soviet Union in response to NASA's space shuttle program, Buran was never intended to be a simple imitation. From its earliest design phase, it pursued capabilities that placed it well ahead of its time, most notably the ability to fly an entire mission without a single human on board. Unlike its American counterpart, Buran was designed for full autonomy. Its onboard computers could handle launch, orbital maneuvering, atmospheric re-entry, and landing without pilot intervention. This was not a theoretical feature or an emergency backup. In 1988, Buran completed its first and only spaceflight entirely unmanned, launching atop the Energia heavy-lift rocket, orbiting Earth twice, and landing precisely on a runway at Baikonur Cosmodrome. At a time when autonomous systems were still primitive by modern standards, the achievement stunned aerospace engineers worldwide. Technically, Buran incorporated several innovations that surpassed existing shuttle designs. It relied on the Energia rocket for launch, meaning it did not carry its own main engines into orbit. This reduced structural stress on the orbiter and increased payload flexibility. Buran could theoretically carry heavier and more varied cargo than the U.S. Space Shuttle, including large military satellites, space station modules, or even other spacecraft. Its thermal protection system was also more modular, allowing for faster inspection and replacement of damaged heat tiles. The shuttle's design reflected Soviet strategic thinking. Military planners envisioned Buran as a multi-role platform capable of satellite deployment, retrieval, repair, and potentially classified defense missions. The option for unmanned flight reduced risk to crews and allowed missions too dangerous or politically sensitive for human pilots. In many ways, Buran anticipated modern spaceflight concepts now seen in autonomous spacecraft and reusable launch systems. Despite its technical success, Buran became a victim of timing rather than engineering. The collapse of the Soviet Union drained funding, political will, and industrial support. Only one orbiter ever flew to space, and the program was officially canceled in 1993. In a final irony, the sole space-flown Buran was destroyed years later when the hangar roof at Baikonur collapsed. Today, Buran is often remembered as a failed rival to the space shuttle. In reality, it was something far more remarkable, a spacecraft designed for an era that had not yet arrived. Its autonomous flight capabilities, modular systems, and heavy lift integration foreshadowed the direction of modern space exploration. The world was not unprepared for Buran because it was flawed, but because it arrived decades ahead of the infrastructure, economics, and political stability needed to sustain it. FV4005 Stage 2, Britain's nuclear-era tank destroyer. The FV4005 Stage 2 stands as one of the most extreme armored fighting vehicles ever conceived, a product of Cold War anxiety and nuclear-era battlefield thinking. Developed by Britain in the early 1950s, this experimental tank destroyer was not designed for maneuver warfare or prolonged engagements. Instead, it was built around a single purpose: delivering overwhelming firepower capable of destroying the heaviest Soviet tanks at long range with a single shot. At the heart of the FV4005 was its astonishing main weapon, a 183mm L4 gun, the largest cannon ever mounted on a tank. This massive gun was intended to fire high-explosive squash head HESH rounds, powerful enough to shatter even the thickest armor through sheer kinetic shock. At a time when intelligence reports suggested Soviet heavy tanks like the IS-3 posed a serious threat to NATO forces, Britain sought a decisive countermeasure rather than incremental improvements in armor or mobility. To accommodate the enormous gun, engineers mounted it on a modified Centurion tank chassis and enclosed it within an oversized, lightly armored turret. The result was a vehicle that looked almost improvised, its towering silhouette betraying its experimental nature. The turret's thin armor offered minimal protection, reflecting the assumption that the FV4005 would operate from long range, strike first, and reposition quickly rather than survive sustained combat. The vehicle's firepower, however, came at significant cost. The massive ammunition was cumbersome, forcing a two-piece loading process that dramatically reduced the rate of fire. Recoil was extreme, placing enormous stress on the chassis and suspension. Accuracy suffered, especially after repeated firing, and the vehicle's height made concealment nearly impossible on the battlefield. In an era moving toward faster, more flexible armored formations, the FV4005 was increasingly out of step with evolving doctrine. By the mid-1950s, advances in anti-tank guided missiles and improved tank gun technology rendered the concept obsolete. Missiles offered long-range armor-killing capability without the logistical and mechanical burdens of an oversized cannon. As a result, the FV4005 never progressed beyond the prototype stage. Only a single Stage 2 vehicle was completed, and it never entered operational service. Yet the FV4005 remains a fascinating example of transitional military thinking. It represented a moment when designers attempted to solve strategic problems with sheer scale and destructive power, before electronics and precision weapons reshaped warfare. Today, the surviving FV4005 prototype serves as a reminder of how close Cold War militaries came to deploying truly extreme machines, vehicles born not from practicality, but from the fear of what the next war might demand. Avro Canada, CF-105, Arrow, the interceptor that terrified the Cold War. The Avro Canada, CF-105, Arrow remains one of the most powerful symbols of unrealized Cold War potential, a fighter so advanced that it unsettled allies and adversaries alike. Developed in the 1950s, the Arrow was conceived to defend North American airspace against high-speed Soviet bombers that threatened to cross the Arctic at unprecedented altitudes. At a time when most air forces were still transitioning from subsonic designs, the Arrow aimed far beyond existing limits. Designed as a twin-engine, all-weather interceptor, the CF-105 was engineered to fly at Mach 2 speeds while operating above 50,000 feet. Its large delta wing provided excellent high-speed stability and climb performance, allowing it to reach interception altitude in minutes. The aircraft's size was intentional. It needed to carry heavy fuel loads, advanced radar, and long-range air-to-air missiles to meet bombers before they reached populated targets. In performance terms, the Arrow rivaled, and in some areas exceeded, contemporary American and Soviet fighters. What truly set the Arrow apart was its systems integration. It was designed around a cutting-edge fire control system that combined onboard radar, computerized targeting, and guided missiles into a single networked package. This concept, now standard in modern air combat, was revolutionary in the 1950s. The Arrow was meant to detect, track, and engage multiple targets in all weather conditions with minimal pilot workload, making it one of the earliest examples of a systems-driven combat aircraft. Early flight tests confirmed its promise. Test pilots praised its handling, acceleration, and stability at high speeds. Even with interim engines installed, the Arrow demonstrated exceptional performance. Its intended power plant, the domestically developed Orenda Iroquois engine, promised even greater speed and altitude capability, potentially making the Arrow one of the fastest interceptors in the world. Despite its success, the program collapsed under political, economic, and strategic pressure. The rising cost of development, shifting defense priorities, and growing faith in surface-to-air missiles led the Canadian government to abruptly cancel the project in 1959. In an unprecedented decision, all completed airframes, prototypes, and much of the tooling were ordered destroyed. Thousands of skilled engineers lost their jobs, many later contributing to aerospace programs in the United States and Europe. The Arrow never entered service, but its legacy endures. It demonstrated that Canada was capable of producing world-class military aircraft and foreshadowed design philosophies that would dominate later generations of fighters. To this day, the CF-105 Arrow stands as a reminder that in the Cold War, technological superiority alone was not always enough to ensure survival. Vespa 150 TAP, the scooter armed to kill tanks. The Vespa 150 TAP is one of the most unconventional military vehicles ever fielded, a striking example of Cold War improvisation driven by necessity rather than elegance. Developed in the 1950s for the French Army, this lightweight scooter was never meant to fight tanks head-on. Instead, it embodied a radically asymmetric approach to anti-armor warfare, using speed, surprise, and portability to neutralize threats far beyond its apparent capabilities. Based on the civilian Vespa 150, the TAP variant, short for Troops Aéroportées, was designed specifically for airborne forces. French paratroopers needed equipment that could be dropped from aircraft, rapidly assembled, and moved across rough terrain immediately after landing. traditional armored vehicles were too heavy and slow to deploy. The Vespa offered a solution: compact, mechanically simple, and easy to transport by parachute or glider. What transformed the Vespa from a utility scooter into a battlefield weapon was its armament. Mounted to the frame was a 75mm M20 recoilless rifle, a proven anti-tank weapon capable of penetrating armored vehicles of the era. The scooter itself was not designed to fire the weapon directly. Instead, it served as a fast delivery platform. Paratroopers would ride the Vespa to a firing position, dismount, set up the recoilless rifle on its tripod, and engage enemy armor from ambush. This concept reflected post-World War II battlefield realities. France, shaped by its experiences in rapid maneuver warfare and colonial conflicts, emphasized mobility and flexibility over heavy firepower. The Vespa 150 TAP allowed lightly equipped infantry to threaten tanks, vehicles, and fortified positions without relying on traditional armored support. Its low profile and agility made it difficult to detect, especially in urban or rugged environments. However, the design came with obvious limitations. The Vespa offered no protection to its rider, and its performance was marginal off-road. Ammunition was limited, and the crew remained highly vulnerable once engaged. The vehicle demanded disciplined tactics and careful coordination, relying entirely on surprise rather than endurance. As anti-tank guided missiles became more widespread in the 1960s, the Vespa's role quickly diminished. Despite its short service life, the Vespa 150 TAP remained significant. It demonstrated how unconventional platforms could be adapted to meet specific tactical needs, foreshadowing modern concepts of light, rapidly deployable forces equipped with powerful standoff weapons. In an era increasingly dominated by heavy armor and large formations, the Vespa offered a reminder that innovation does not always come in imposing shapes. Today, the Vespa 150 TAP is remembered less as a practical weapon and more as a symbol of creative military thinking, proof that even a humble scooter could be repurposed into a tool capable of threatening the most feared machines of its time. Object 279, the Soviet tank built for nuclear battlefields. Object 279 was not merely a tank, it was a battlefield theory made of steel, engineered for a future shaped by nuclear war. Developed by the Soviet Union in the late 1950s, this experimental heavy tank was designed with a grim assumption in mind. The next major conflict would involve atomic weapons, radioactive fallout, and shattered terrain. Where most tanks were built to fight other tanks, Object 279 was built to survive the end of the world. At first glance, its design appears almost alien. The tank featured an elliptical, saucer-shaped hull with extremely sloped armor, intended to deflect incoming shells and shockwaves from nuclear blasts. This shape was not aesthetic experimentation. It was calculated to reduce the effects of overpressure and prevent the vehicle from being flipped or buried by blast forces. The armor itself was exceptionally thick, reaching levels that rendered contemporary anti-tank guns largely ineffective. Perhaps the most unusual feature of Object 279 was its 4-track suspension system. Instead of the conventional 2 tracks, the tank rode on 4 independently mounted tracks, distributing its massive weight more evenly across the ground. This allowed it to traverse soft, cratered or irradiated terrain that would trap or immobilize standard armored vehicles. Soviet engineers envisioned battlefields littered with debris, mud, and blast craters, conditions where mobility would be just as critical as protection. The tank was armed with a powerful 130mm gun, capable of destroying any NATO armor of the era at long range. An advanced autoloader reduced crew workload and increased rate of fire, while the internal layout emphasized crew survivability. Object 279 also incorporated a nuclear, biological, and chemical NBC protection system, sealing the crew inside a pressurized environment to shield them from radioactive dust and toxic fallout. For its time, this level of protection was extraordinary. Despite its technical ambition, Object 279 was deeply impractical. Weighing nearly 60 tons, it was expensive, complex, and difficult to maintain. The four-track system, while innovative, introduced mechanical vulnerabilities and logistical challenges. As Soviet doctrine shifted toward faster, more versatile main battle tanks, and as nuclear war scenarios became less tank-centric, the rationale for such a specialized vehicle weakened. In 1960, the program was canceled before Object 279 could enter service. Only a single prototype was completed, preserved today as a museum piece rather than a weapon of war. Yet, its significance endures. Object 279 represents a moment when military planners attempted to engineer certainty into an uncertain future. It was a tank designed not just to fight in war, but to operate in the aftermath of annihilation. An extreme solution for an extreme age. XB-70 Valkyrie, the Mach 3 bomber that flew too far ahead. The XB-70 Valkyrie was one of the most ambitious military aircraft ever built. A strategic bomber conceived at the height of Cold War tension and engineered to outrun the future itself. Developed by North American Aviation in the late 1950s, the Valkyrie was designed to fly faster, higher, and farther than any bomber before it. Its mission was simple in theory, but extreme in execution: penetrate Soviet airspace at Mach 3 above 70,000 feet and deliver nuclear weapons before enemy defenses could respond. At a time when most bombers relied on altitude or electronic countermeasures for survival, the XB-70 relied on raw speed. Its sleek, futuristic airframe was built to sustain prolonged flight at 3 times the speed of sound, generating temperatures that required extensive use of stainless steel and titanium rather than conventional aluminum. The aircraft's distinctive delta wing and drooping wingtips were not stylistic flourishes. They exploited compression lift, using shockwaves generated at supersonic speed to improve aerodynamic efficiency. Powered by 6 massive afterburning turbojet engines, the Valkyrie promised intercontinental range and unprecedented performance. It could theoretically cross the Atlantic faster than many fighters could climb to intercept it. In strategic terms, the XB-70 represented the ultimate expression of manned bomber dominance, a platform that would render surface-to-air missiles and interceptors obsolete through speed alone. However, the world changed faster than the Valkyrie could enter service. By the early 1960s, advances in Soviet radar, high-altitude surface-to-air missiles, and interceptor aircraft undermined the assumption that speed and altitude guaranteed survival. At the same time, intercontinental ballistic missiles emerged as the preferred nuclear delivery system, offering faster response and lower political risk than manned bombers. The strategic logic that justified the XB-70 began to collapse. Only 2 prototypes were ever built. Flight testing confirmed the aircraft's extraordinary performance, but also revealed its immense cost and complexity. In 1966, one of the prototypes was lost in a mid-air collision during a publicity flight, further eroding political support. The program was canceled before the Valkyrie could be operationally deployed. Yet, the XB-70 was far from a failure. It became a flying laboratory, generating invaluable data on high-speed aerodynamics, materials science, and supersonic flight. Lessons learned from the Valkyrie influenced later aircraft designs, including reconnaissance platforms and advanced fighters. In retrospect, the XB-70 Valkyrie was not flawed. It was simply premature. It was a bomber built for a strategic environment that vanished before it could arrive. As a result, it stands today as a symbol of Cold War ambition, a machine that reached breathtaking heights only to be overtaken by the rapid evolution of warfare itself. Kugelpanzer, the mystery rolling fortress of Nazi Germany. The Kugelpanzer remains one of the most enigmatic armored vehicles ever produced. A machine so unconventional that its true purpose is still debated decades after its discovery. Developed in Nazi Germany during the later years of World War II, the Kugelpanzer, literally ball tank, defied every established principle of armored warfare. Instead of tracks, turrets, or heavy firepower, it relied on an almost spherical shape and minimal armament, raising questions that historians continue to grapple with. Physically, the Kugelpanzer was strikingly small and simple. The vehicle consisted of a steel spherical hull mounted on two large wheel-like shells with a narrow central ridge for stability. A small rear roller provided balance, while a tiny engine powered its slow movement. The operator sat inside the cramped interior, viewing the outside world through narrow vision slits. Armor thickness was minimal, suggesting the vehicle was never intended to withstand direct combat with tanks or anti-armor weapons. What makes the Kugelpanzer truly mysterious is the absence of clear documentation. No official German records definitively explain its role, and no combat reports mention its use. The only surviving example was captured by Soviet forces in Manchuria in 1945, far from Germany itself, implying it may have been exported to or tested by Japan. Today, that lone vehicle resides in a Russian museum, offering more questions than answers. Several theories attempt to explain its intended function. Some historians suggest it was designed for reconnaissance, using its low profile to observe enemy positions under fire. Others believe it may have been intended as a mobile observation post, artillery spotter, or even a protected vehicle for laying communication cables. More speculative interpretations propose it as a suicide vehicle or psychological weapon, though there is no evidence to support such claims. Technologically, the Kugelpanzer was ahead of its time in concept rather than capability. Its rounded shape would have deflected small arms fire and blast waves more effectively than flat surfaces, an idea echoed decades later in certain riot control and experimental armored designs. However, its slow speed, poor visibility, and lack of offensive power made it impractical for real-world battlefield conditions. The Kugelpanzer never influenced armored doctrine and never progressed beyond prototype status. Yet its existence highlights the desperation and experimentation that characterized Germany's late war weapons programs. As resources dwindled and defeat loomed, engineers explored increasingly unconventional ideas in search of a breakthrough. Today, the Kugelpanzer endures as a historical anomaly, a rolling fortress with no clear mission, frozen between innovation and absurdity. It stands as a reminder that not all advanced ideas are successful, and that even the most radical designs can vanish into obscurity without ever proving their worth. Page 1000, Rata, the land battleship that never reached war. The P-1000 Rata was not a tank in the conventional sense. It was a vision of battlefield dominance taken to its absolute extreme. Conceived in Nazi Germany during World War II, this proposed super-heavy armored vehicle was intended to function as a land battleship, combining naval-scale firepower with armored mobility. Had it been built, the Rata would have dwarfed every tank ever constructed, redefining the limits of what ground warfare could support. Planned to weigh approximately 1,000 tons, the Rata was designed around a massive hull, capable of mounting a naval gun turret taken directly from a Kriegsmarine warship. Its primary armament was to consist of two 280mm naval cannons, weapons normally reserved for heavy cruisers, capable of engaging targets miles away. Secondary armament included anti-tank guns, multiple machine guns, and anti-aircraft weapons, effectively turning the vehicle into a mobile fortress bristling with firepower. In theory, the Rata would have been nearly unstoppable from the front. Its armor thickness was projected to exceed anything fielded by Allied forces, making it virtually immune to standard anti-tank weapons. Designers imagined it advancing slowly across the battlefield, destroying fortifications, armor, and infrastructure with impunity. The psychological impact alone was expected to be immense, reinforcing the Nazi emphasis on intimidating wonder weapons. Reality, however, was far less accommodating. The logistical challenges of operating a 1,000-ton vehicle were insurmountable. The Rata would have required specialized infrastructure, including reinforced bridges, roads, and supply lines that simply did not exist. Its fuel consumption would have been enormous, and its size made it an ideal target for air attack. Even if armor could resist shells, no amount of steel could protect it from sustained bombing. Mobility was another critical flaw. Despite proposals to use multiple marine diesel engines to power the vehicle, its top speed would have been extremely limited. Turning, river crossings, and urban movement would have posed constant obstacles. Far from dominating the battlefield, the Rata risked becoming an immobile liability. By 1943, Germany's strategic situation made such extravagance impossible. Scarce resources, constant bombing, and shifting military priorities forced the cancellation of the project before construction began. The Rata never left the drawing board. Today, the P-1000 Rata stands as a symbol of excess and miscalculation, a weapon conceived without regard for practical warfare. It represents the moment when ambition eclipsed reality, and when the idea of overwhelming power ignored the fundamental truth that war is won through adaptability, not sheer size. Convair SeaMaster, the supersonic jet bomber that took off from water. The Convair SeaMaster was one of the most unconventional strategic aircraft ever developed, a supersonic jet bomber designed to operate not from runways, but directly from the open ocean. Conceived during the 1950s at the height of Cold War nuclear anxiety, the SeaMaster represented the U.S. Navy's attempt to secure a survivable nuclear strike capability independent of vulnerable land bases. In doing so, it pushed aviation technology into territory the world was not yet prepared to sustain. Officially designated the P-6Y, the SeaMaster was a large, swept-wing flying boat powered by 4 jet engines mounted high above the wings to prevent water ingestion during takeoff. It was designed to skim across the sea at high speed, lift off from rough waters, and fly at near supersonic speeds toward its target. This alone set it apart. No other bomber combined jet propulsion, nuclear payloads, and true seaplane operations on such a scale. Strategically, the concept was bold. Naval planners feared that Soviet first strikes could destroy fixed air bases before bombers could launch. The SeaMaster offered a solution by dispersing nuclear bombers across the world's oceans, supported by mobile seaplane tenders and refueling ships. In theory, this made the force nearly impossible to neutralize preemptively. The aircraft could carry nuclear weapons or naval mines and strike deep inland or disrupt enemy sea lanes. Performance figures were impressive. The SeaMaster was designed to approach Mach 0.9 at low altitude and even higher at altitude, with a range suitable for strategic missions. Its avionics and navigation systems were advanced for the era, reflecting its role as a frontline nuclear delivery platform rather than a patrol aircraft. However, technical challenges quickly mounted. Operating large jet aircraft from saltwater environments proved punishing. Corrosion, spray ingestion, and maintenance demands exceeded expectations. Early prototypes suffered from serious stability issues, including violent pitch-up tendencies at high speed. 2 aircraft were lost in fatal crashes during testing, raising concerns about the design's safety and maturity. More importantly, the strategic landscape shifted beneath the program. By the late 1950s, submarine-launched ballistic missiles emerged as a far more survivable and reliable naval nuclear deterrent. Compared to missile submarines, the SeaMaster was expensive, complex, and vulnerable to interception once airborne. The Navy's focus pivoted rapidly, leaving the SeaMaster without a clear future. In 1959, the program was canceled before reaching operational service. Only a handful of prototypes were built. Despite this, the Convair SeaMaster remains a remarkable technological milestone, a supersonic flying boat that attempted to merge strategic bombing with maritime mobility. It was a visionary answer to a fleeting problem, overtaken not by failure of engineering alone, but by the swift evolution of nuclear strategy itself. Flettner Fl 282, the combat helicopter before helicopter warfare. The Flettner Fl 282 Colibri occupies a unique place in military aviation history as one of the world's first truly practical combat helicopters, developed before helicopter warfare had even been fully imagined. Created in Nazi Germany during World War II, the Fl 282 demonstrated capabilities that would not become standard until decades later, making it a machine far ahead of its operational context. Designed by German engineer Anton Flettner, the Fl 282 featured an unconventional intermeshing rotor system, with 2 counter-rotating blades mounted on angled masts. This eliminated the need for a tail rotor, improving stability and control while simplifying mechanical complexity. The design proved remarkably effective, giving the Colibri excellent maneuverability, low-speed handling, and the ability to hover with precision, traits that fixed-wing aircraft could not match. The helicopter was originally conceived for naval use, particularly for reconnaissance and artillery spotting. Operating from ships and confined areas, the FL-282 could take off and land vertically, track enemy movements, and relay targeting information in real time. This role foreshadowed modern helicopter reconnaissance and battlefield coordination, concepts that were largely undeveloped during the early 1940s. In testing and limited operational use, the FL-282 performed exceptionally well. Pilots praised its stability, even in poor weather, and its ability to fly safely at very low speeds. The helicopter could be flown solo or with an observer seated behind the pilot, allowing it to function as a mobile observation platform. Plans were even made to arm later variants with machine guns or light weapons, signaling its potential evolution into an armed combat helicopter. Despite its promise, the FL-282 was a victim of circumstance rather than design. Germany's collapsing wartime industry struggled to prioritize helicopter production amid shortages of materials and constant Allied bombing. Although over 1,000 units were planned, only a small number, estimates range from 24 to fewer than 50, were actually completed. As a result, the helicopter never saw widespread deployment or doctrinal integration. The true significance of the FL-282 lies in what it anticipated. It proved that helicopters could be reliable, versatile, and militarily valuable long before most air forces accepted the concept. Post-war Allied evaluations of captured German rotorcraft, including the FL-282, directly influenced helicopter development in the United States and elsewhere. Many of its design principles resurfaced in later generations of rotary wing aircraft. Today, the Flettner Fl 282 is largely forgotten outside specialist circles, overshadowed by jets and rockets of the same era. Yet it stands as a quiet milestone, a combat helicopter born before the battlefield knew how to use it. In many respects, the Colibri was not merely experimental, it was premature, arriving years before military doctrine could catch up to its potential. Maus, super heavy tank, when engineering outpaced reality. The Maus super heavy tank stands as one of the most extreme examples of military engineering, driven beyond the limits of practicality. Conceived in Nazi Germany during World War II, the Panzer Kampfwagen 8 Maus was envisioned as an indestructible breakthrough vehicle, an armored colossus capable of advancing under fire while annihilating anything in its path. In reality, it became a symbol of how ambition and ideology can outpace battlefield reality. Weighing nearly 190 tons, the Maus was the heaviest tank ever constructed. Its armor was unprecedented, up to 240 millimeters thick on the turret front, rendering it virtually immune to all Allied anti-tank weapons of the time. This level of protection reflected Germany's late-war obsession with survivability through sheer mass, particularly as Allied air superiority and numerical advantage tightened around the Reich. The Maus was meant to be unstoppable, even in the face of overwhelming fire. Its armament matched its bulk. The primary weapon was a 128mm KK-44 L-55 gun, capable of destroying any Allied tank at extreme ranges, paired with a secondary 75mm cannon for closer engagements. On paper, the Maus could dominate any armored confrontation. Few enemy vehicles could even hope to penetrate its armor, while the Maus could destroy targets long before they came close. However, the tank's enormous size introduced crippling problems. Mobility was severely limited. Despite powerful engines, the Maus struggled to exceed walking speed. Most bridges could not support its weight, forcing engineers to propose underwater river crossings using snorkels and electrical cables, solutions that were complex and tactically risky. Fuel consumption was enormous, and transporting the tank by rail required disassembly and specialized infrastructure. The strategic environment further undermined the concept. By the time the Maus prototypes were completed in 1944, Germany lacked air superiority, fuel, trained crews, and industrial capacity. Heavy tanks that could not move quickly or be concealed were easy targets for aircraft. No matter how thick its armor, the Maus could not defend itself effectively against sustained air attack, which had become the dominant force on the battlefield. Only 2 prototypes were built, and neither saw combat. As Soviet forces advanced, the Germans destroyed the vehicles to prevent capture, though the Red Army later recovered and assembled a single example for evaluation. Today, that reconstructed Maus sits in a museum, silent testimony to its creator's ambitions. The Maus was not a failure of engineering skill, it was a failure of strategic judgment. It demonstrated what was technically possible, but ignored what was operationally viable. In the end, the Maus proved that war is not won by the biggest machine, but by the one that balances firepower, mobility, and realism. A lesson learned too late. Project Pluto, the nuclear-powered missile that should never fly. Project Pluto was one of the most terrifying weapons concepts ever seriously pursued. A nuclear-powered cruise missile designed not just to strike a target, but to devastate everything in its path. Developed by the United States during the Cold War, Pluto represented a moment when strategic desperation and technological confidence collided, producing a weapon so destructive that it was ultimately deemed too dangerous to deploy. At the core of Project Pluto was the Supersonic Low-Altitude Missile, or SLAM. Unlike conventional missiles powered by chemical fuel, SLAM was designed to use a nuclear ramjet engine. Air rushing into the missile at supersonic speed would be heated directly by an unshielded nuclear reactor, then expelled to generate thrust. This eliminated the need for fuel tanks and theoretically allowed the missile to fly for days or even weeks without refueling. The implications were staggering. SLAM was intended to fly at Mach 3, hugging the terrain at extremely low altitude to evade radar detection. As it traveled, it would scatter radioactive exhaust across the landscape below. Upon reaching enemy territory, it could release multiple nuclear warheads before continuing onward, crashing only after completing its mission. Even without detonating its weapons, the missile itself would function as a flying radiological weapon. From a technical standpoint, Project Pluto was remarkably successful. Engineers built and tested the nuclear ramjet reactor, named Tori, in the Nevada desert. Tests demonstrated that the reactor could operate at extreme temperatures while producing the necessary thrust. In purely engineering terms, the concept worked. Few Cold War projects so clearly demonstrated the gap between what could be built and what should be used. Yet, the very features that made SLAM attractive also made it strategically and morally indefensible. The missile could not be recalled once launched. Its flight path would contaminate Allied and neutral territory as easily as enemy land. Testing a fully operational system posed enormous environmental risks, and any accidental crash would result in severe radioactive contamination. Moreover, its indiscriminate nature conflicted with emerging doctrines that sought at least nominal control over nuclear escalation. By the early 1960s, the strategic environment had shifted. Intercontinental ballistic missiles offered faster, more controllable nuclear delivery without continuous radiation exposure. Advances in air defense and detection further reduced the theoretical advantages of a low-flying nuclear missile. In 1964, Project Pluto was canceled, not because it failed, but because it succeeded too well at embodying worst-case warfare. Project Pluto remains a stark reminder of Cold War excess. It was a weapon designed for total annihilation, built with little regard for consequences beyond victory. Today, it stands as a chilling example of how technological brilliance, unchecked by restraint, can lead to creations the world is better off never seeing fly. Ekranoplan, the ground effect, warship that defied classification. The Ekranoplan was neither a ship nor an aircraft, but something entirely in between, a hybrid war machine that challenged traditional military classification. Developed by the Soviet Union during the Cold War, the Ekranoplan exploited a little-known aerodynamic phenomenon called ground effect, allowing it to skim just meters above the surface of the sea at extraordinary speeds. In doing so, It promised to rewrite the rules of naval warfare before the world was ready to adapt. Ground effect occurs when an aircraft flies very close to a surface, creating a cushion of high-pressure air that increases lift and reduces drag. Soviet engineers realized that vehicles designed specifically to operate in this narrow altitude band could achieve speeds far greater than conventional ships while carrying payloads rivaling small naval vessels. The result was the Ekranoplan, a massive, winged craft capable of racing over water at speeds exceeding 300 kilometers per hour, well beyond the reach of traditional surface combatants. The most famous example was the Caspian SeaMaster, a colossal prototype that stunned Western intelligence when satellite images first revealed it in the 1960s. Even more alarming was the Lund-class Ekranoplan, an operational military variant armed with 6 large anti-ship cruise missiles mounted on its nose. Flying low enough to evade radar detection, the Lund was designed to strike enemy carrier groups with little warning, combining the surprise of an aircraft with the firepower of a missile boat. Strategically, the Ekranoplan occupied a dangerous gray zone. It flew below most radar horizons, was too fast for naval guns to track easily, and too large and low-flying for conventional air defenses optimized for higher altitude targets. Its range and payload made it ideal for rapid coastal strike missions, amphibious support, and long-range missile delivery across enclosed seas, such as the Caspian or Black Sea. However, the same characteristics that made the Ekranoplan formidable also limited its practicality. It was highly sensitive to sea state, struggling in rough weather or high waves. Its enormous size made maintenance complex and costly, while its specialized mission profile reduced flexibility. Additionally, because it did not fit neatly into naval or Air Force doctrine, responsibility for funding and operational control was often unclear. As the Cold War ended, economic collapse and shifting military priorities sealed the Ekranoplan's fate. Only a handful were ever built, and most were eventually abandoned or scrapped. Yet the concept itself never truly disappeared. Today, the Ekranoplan is recognized as a machine ahead of its time, a bold attempt to exploit physics for strategic advantage. Modern interest in ground effect vehicles for military transport and rapid strike roles suggests the idea was not flawed, merely premature. The Ekranoplan defied classification because it belonged to a future that never fully arrived.